I'm happy to introduce Hongcheng Wang from Comcast. He's going to speak to us about architecting a smart home monitoring system and the design decisions that go into the system architecture from edge to cloud.
So good afternoon, everyone. Welcome to my talk. So my name is Hongcheng Wang. I'm leading the computer vision and deep learning research team at Comcast Applied AI Research. So at Comcast Applied AI Research, we basically use deep learning, natural language processing, and computer vision to support, to improve our products, which includes Xfinity TV, high-speed internet, smart home, and customer service. And also we do some work for Universal Pictures and Universal theme parks, which is also a part of Comcast business. So specifically, our research is 4 themes. The first one is we do a lot of work on NLP and voice understanding. So how many people are using Xfinity TV? Okay, good. Do you have voice remote control? Yeah. If you do not have that, so please ping me after the talk, or go online. So we will ship one to you for free. Right. So the voice-based remote control is amazing. We just won the 2017 Emmy Award in the technology category. So the second thing is we do computer vision. So basically, we do media analytics and video analytics for smart home. For media analytics, so we use computer vision to understand what's happening in the broadcast videos to get the scene level tagging, for example, events, faces, activities, or topics. And for video analytics, Xfinity Home has like millions of cameras deployed in the residential home. So we basically use computer vision to understand what's happening in people's home and alert you if there's something abnormal happens. And the third topic is content discovery. So basically, we use machine learning to do recommendation and personalization and recommends the specific relevant content only to you. And finally, we do machine learning and deep learning for big data analytics and also for customer service applications. So all these technologies are interfaced with our voice-based remote control such that we can provide end-to-end enhance the user experience from entertainment to home security. Right? So this talk I will focus about the smart home applications. So Comcast is becoming a leading platform to integrate smart home technologies with millions of cameras. So our camera has 24/7 recordings, continuous video recording, and our customer can view the live view and also browse all the events based on the smart thumbnails, which is representative of each event. And you can also do semantic search and do object filtering based on what kind of object you are interested. So besides cameras, Xfinity Home also provides door and window sensors. We also integrate Wi-Fi signals, remote control signals, and also maybe voice information. And by fusing all this data, which allows us to do anomaly detection. So our team is also responsible for the big data analytics from all these sensors for smart home. So what our customers cares. So as homeowner, as our customer, you may care about when your kids came back from school, or you may care about if a stranger come to your home, right? Or you may care about the cleaning people, the maintenance people, when they come to your home, when they left. Or you may also care about the activities of your dog or pet or cats when you are not at home. And you also care about when the package is delivered to your home, or when a USPS or FedEx truck pulled over to your home. So, and also any anomalies, you may want to get a notification, right? So this requires better understanding of what's in the video. So who is in the video? What are they doing, right? So we believe that for such a big system, we have millions of cameras. For such a big system, a hybrid system would do the job, right? So in the following slides, I will talk about how to design, what's the trade-off of designing a hybrid system. So in order to design a hybrid system, we need to consider several factors. One is the video resolution, what kind of video resolution you have. Maybe for face recognition, you want to detect faces on the edge or on the cloud. And the CPU or GPU, do you have GPU chips on your camera? And do you use CPU or GPU on the cloud, right? So this all drives the cost and also your requirements. So what a bandwidth? What's the bandwidth of your data from the camera to the cloud? And what kind of algorithm? Are you using deep learning or using more traditional algorithms? So all these factors should be considered simultaneously in order to build a cost-effective system. So the general guideline is to push as much computation as possible to the edge, because everything running on the cloud would be extra for our business. So for Comcast Xfinity Home, our camera resolution is 720p. So though our next generation cameras has higher resolution, so we do not have the GPU chip on the camera yet, right? So that's why at this point it's hard to push some of the deep learning algorithms onto the cloud, onto the edge. So a hybrid system makes more sense for us. And let's take a look at the advantages of running analytics on the edge. So we have millions of cameras, but each of the camera has limited processing. And also, if we do analytics on the edge, we can extract high quality video frames, metadata. So of course, this will also reduce the bandwidth of the metadata. So in contrast, running video analytics on the cloud would theoretically have unlimited resources. Theoretically, we can deploy as complex algorithm as we want, but there's always a cost associated to that, right? For a system, like millions of cameras, and if you run deep learning using GPU, it would be very cost prohibitive. So we want to fully utilize all these resources on your GPU machine. So I will discuss later. So let's take a look at what we put on the edge and on the cloud. So for the edge, we use simple analytics functionalities. For example, motion event detection and smart thumbnail. So for smart thumbnail, we get high quality thumbnail, which can be used to represent all the motion events. And also we can use those thumbnails to do object detection, which can get better results. And face detection, we can extract the face images from the raw image and then put to the cloud for face recognition. And also, of course, we also have video and audio analytics, which we can detect glass breaking and alarming, right? And so more advanced algorithms, for example, like anomaly detection, deep learning-based object detection, summary of my day, face recognition, and even activity recognition is running on the cloud. So I will talk about a specific use case called semantic video search. So each of our customers has 10 to 30 days of videos stored on the cloud. So on average, there are more than 100 events per camera per day. So it's very hard for them to find a specific video clip by just browsing. So we basically use the computer vision technology to tag each video event with the object, event, and also their attribute. So our customer can use their voice to do semantic search. For example, if they want to find is there, when the school bus comes, or show me all the person events yesterday, right? So our app will automatically deliver those relevant events to you. So here's the hybrid architecture we use for semantic video search. First of all, we run simple video analytics and generate the metadata, which includes the thumbnails, motion frames, and tracker ID and the motion bounding box. The video and the metadata will be stored to the continuous video recording storage. So whenever there's a motion event, we basically run XCV, we call Xfinity Computer Vision, object detector, and event recognition. So this module will take into the metadata from the camera and generate a deeper metadata, which includes the object events and object attributes such as color. This deeper metadata will be stored into a database, for example, Cassandra database. And then the NLP module, the natural language processing module, interface with the Xhome client. So it takes the user's semantic query and map to the metadata in our metadata database, and then retrieve the relevant events to the end user. So there are three key components. One is the camera metadata. The other is efficient algorithm. And third one is the computing resource optimization. So all these three components are important, are critical for us to develop a robust but cost-effective solutions. So in the following slides, I will discuss these three aspects in more detail. So first of all, what metadata we extract from the camera? So as I mentioned, our video resolution is not that high, and the video compression makes image quality worse in order to save the bandwidth. So we could use the original image frame to do the object detection, but it's very costly. Or we can resize to a smaller size, such that smaller objects may not be detected. So what we do is we crop the object out based on the motion information, and use those as the input to the object detector. So this is by running a multi-buffer parallel processing. So video analytics running on the low resolution videos, and the image thumbnail is cropped from a high resolution image buffer. So we'll do some experiment to show how this scheme works. So before we do the evaluation, I want to talk about the relevance-based evaluation metric. So for surveillance videos, not all the events are equal. So we basically categorize all those events into 6 categories from 0 to 5. Right? For 0, mostly it's rain, snow, or rain, snow, wind, or shadows. All these events we definitely do not want to send to the customer. Relevance 1 means insignificant objects like the bugs or squirrels, right? So maybe you send these events to the customer maybe is okay, right? So at least think your camera is doing his job. Relevance 2 means significant objects, for example, a car passing by, on the street, which is not on your property, right? So, and relevance 3 and 5 is something happens in your property, right? 4 means significant, objects which come to or exit your property. 5 is something definitely you want to get a notification for the customer, like a burglary or special events. So as a user, you do not want to have relevance 0 events. And also for relevance 4, we do not miss that, right? So if we miss that will be look very bad. If somebody come to your home, we didn't detect that. So that's why we use different relevancy to evaluate the algorithm. For precision, we use relevance 1 and above. For recall, we use relevance 4 and above. So here is the benchmark results for object detector using original resized image frame versus the cropped image frame from the camera. And we showed that, by the way, this is the data set we curated in ourselves at Comcast. So it's a very challenging data set, which includes day and night, rain, snow, a lot of challenging data set. So we draw the precision recall curve on the same, on different plot. So the solid line shows the results using the resized, using the cropped thumbnails. And the dotted line is using the resized original frames. So we can show that the cropped frames consistently generate better results in terms of precision, the recall. So this shows basically the importance of the metadata, what kind of metadata we need to extract from the camera. And the other is the CPU usage, so CPU and GPU optimization. So we so basically for this kind of system, right? So we have our GPU machine on the cloud includes 6 CPU cores for each GPU core. So how can we leverage all these resources to make sure the GPU is fully utilized, because GPU is much more expensive. So we basically make this, we use a multi-thread parallel processing, put some of the tasks running on CPU, some of the tasks running on GPU. So only, for example, some pre-processing and post-processing are running on the CPU, and the object detection based on deep learning is running on the GPU, such that we make sure all the GPU are fully utilized. So we do a trade-off study of using the select different metadata, and also the CPU GPU time, and also the accuracy. So the left solid X is the accuracy used in terms of F-score, which is a combination of precision and recall. And the right X is the CPU or GPU time in terms of millisecond. The horizontal X is the number of frames we selected for a 15-second video, each with 10 frames per second. That means 150 frames per video clip, per event clip. So we can say that when we select 5, more than 5, 5 and above, the accuracy does not change much, basically the two solid curves as shown here. And the dotted line, the dotted curve shows the computing time. So we want to make sure the GPU time is more than the CPU time. If we run six cores, means 6 CPU time. All the time on CPU, no more than the GPU usage. So we found a sweet spot, which is using 5 frames and using the GPU only. We do not need to consider the video loading time, which is running on the CPU, which is negligible. Okay, so the third effort we are doing is the efficient algorithm on the cloud. So as we know, the traditional algorithm is background subtraction and object detection. So in order to save the cost of the cloud, so we think this is not enough. So first of all, it's not efficient. So it's so basically, if you run a video clip, which is 15-second video, using the original resolution, original frame rate, so we use one of the state-of-the-art methods, for example, the faster RCN, we get 15 seconds per video clip. And the model size is 100 to 400 megabytes. Although we already optimized to 100 milliseconds per event, still it's not enough. There's still space to improve. And also that it's not robust. We still have a lot of false detections and misdetections because we are not fully leverage the spatial and temporal information in the video. And also the parameter tuning. For each of these stages, there's at least one parameter associated to that. It's very hard to tune a good system. For that, we basically developed a remote net, a relevant motion event detection framework. So in this framework, we explore the properties of a home surveillance video. Basically, relevant motion is sparse, both spatially and temporally. So we encourage the network to learn to focus on the moving object. So first of all, the video is subtracted from the reference frame, which is, for example, a background image. And then we run 5 layers of 3D convolutionalness using spatial-wise max pooling. And then we enforce a spatial temporal attention layer, which is another 3D convolutional layer. And then we apply another 4 layers of 3D convolutionalness, which is focused on temporal-wise maximum pooling. And finally, we use the global average pooling, which aggregate all the spatial features. They apply several one by one convolutions, which is generated by the binary decision. So the use of global average pooling, spatial global average pooling, and also the one by one convolutions will reduce the number of parameters in the model and also reduce the size of the model. So, and the advantage is it's an end-to-end network. Parameter tuning is much simplified, and it's very efficient, and also the model size is very small. So I will show you some of the results we generated here. So we did some benchmark comparison with the traditional methods with some of the state-of-the-art object detectors, such as faster RCN, single-shot detector, and also we compare the original convolutional 3D network. So we basically tune the traditional methods using the best parameters we can achieve. So our model with the reference frame detection and the spatial temporal attention model, we achieve the best results as shown in the blue curve in this precision recall curve. Basically, the higher, the better. And more importantly, the remote net has much smaller model size and faster speed. So you can see that the remote net 1 and remote net 2, at least we get 450 times speed reduced model size, and also for the GPU speed, we can reduce to 4 milliseconds per video event, which is more than 1,000 times speed up compared to traditional method. And for CPU, we also get like 0.2 millisecond per event, which is very impressive. And we are also in the progress of implementing that on the edge. So currently it's on the cloud. So here's some visual results. Basically, the top row shows the failure cases of traditional methods, but is successfully detected using our remote net. So the first video is a false detection from a traditional method. So basically, a person walks through a car. So it's detected as a car motion event. And the second is two persons walking in the shadow is not detected by the conventional events method. The last two examples is the failure cases of our model. So the first one is a person standing there, more or less, there's a limited motion. The second one is a bird basically landing there and moving. So hope I can play the video. Oh, sorry. Yeah, for some reason, the video is not playable. Okay, so take-home messages. So for a system with millions of cameras, so we need to push as much computing as possible to the cloud. And for cloud computing, there's a lot of space for us to work towards reduce the cost. What we do is for one, we get the high-speed metadata directly from the camera. Secondly, we optimize the CPU and the GPU usage, which can fully leverage the GPU resources. And the third one is we use more efficient algorithms to reduce the cost of object detection. Okay, thank you.
Excellent. Thank you. Does anyone have any questions for Hongcheng?
Yes, please.
Do you have dedicated hardware for each customer, or does it go into a generalized cloud? And how elastic are the resources for each instance of security that you're setting?
We have, so for the computing resources, we do not have a specialized resources for each customer, basically. We aggregate all the events, running, basically use the Kubernetes to make it scalable on the system. Whenever there's a motion, if it comes in, we do deep learning analysis and get the results put into the database. Yeah. Yes?
Yeah, what do you find to be the most important or useful information that's coming from your cameras as far as metadata?
What do you find the most useful information directly for as far as metadata from the camera? So the metadata from the camera, so it really depends on the goal, right? So our goal is to reduce the cost, to reduce the bandwidth. So we think the information from the camera, like reduce the number of frame rates, reduce high quality thumbnails, extracted directly from the raw images are very important for robustness of the algorithm, for the accuracy of the algorithm, and also in terms of the computing on the cloud, we can directly load some of the images or some of the low frame rate videos. We can save time and save cost. We are not using motion vector. We just use the bounding box. Yeah.
So what was the difference between the RemoteNet 1 and RemoteNet 2? I think you had that in one of your...
Yes, RemoteNet 1 is the reference frame plus C3D, convolutional 3D network. And RemoteNet 2, we have the spatial temporal attention model enforced. So that's why RemoteNet 2 is more it's more accurate, but less. The model size is a little larger, and also the computing time is slower.
Okay, thank you.
For your data set, how did you gather the data, and how big of a data set did you use? How did you label it? What kind of steps did you take there?
That's a good question. So basically, we are not allowed. First of all, we are not allowed to access any data from the customer. The good thing is, within Comcast, we have a big trial group. Whenever there's a camera, a new version or new features come out, our employee get first look into that. Basically, we get free cameras for the employee, and we ask the employee to donate videos. So we have thousands of cameras in the field, basically. We label ourselves. We have internal data labeler, because even for the employee, they do not want their videos to be, make it public, right? Or by some third-party companies to do that. Yeah. The data we have several hundred cameras. For each camera, we can have months or days data, right? But we curate a special data set, which is like tens of thousands of events, basically. Yeah.
Okay.
It's very time-consuming. Yeah.
If you have a GPU powered or some SoC powered cameras, how would you adjust your processing to cover the functionality you would implement?
If you have a GPU powered camera, right? That's something we are still doing the research. Basically, it really depends on the use case, right? So what kind of user experience you want to provide to the customer, right? So I do not have general comments on that, unless you have some use case, right? So to justify why we need to put some of the stuff on the camera, what's the cost of the GPU chips on the camera? Because we think about the millions of cameras, it's a big cost for the company, and also maybe for the customer eventually.
Yeah, I wasn't going to ask for the cost. I was asking if even for your current use case.
Yeah.
Right. For example, if you were to have the GPU on the cameras, how would this processing model look like?
I would like to put the object detection on the camera, basically, right? So, but still, we generate metadata push to the cloud, which allows to the retrieval, right? So we do not put the metadata onto the camera. The object detection, definitely. The face recognition, I'm not sure yet at this point. Depends how much GPU resource you can use, right?
Thank you.
Thanks.
Okay, so last question.
Yeah, I have a question regarding I think you call them the relevance levels of your events, and I'm really interested in relevance number 5, which is the highest one, which didn't have a lot to do with video analytic or things like that. It's more like behavioral and what's going on in the scene. If you're trying to detect robberies and really abnormal things going on. So I'm guessing that there's humans in the loop at some point in some of the judgment calls that have to happen here. Wondering if you could talk about that. Do you have humans look at every single feed that's coming in here? How are they triggered to look at some of that? Or am I off base and there are no humans involved at all?
Yeah, we do not have human in the loop to do that. I mean, we are still basically put some of the features like people can thumb up, thumb down to the app. We do not have that feature yet. But
so that case where you alert.
Relevance 5, when we say relevance 5, we say fire, burglary, or some special event. So special event, which I mean is kind of anomaly detection. All the anomalies we detected from the customer. So basically, which includes all the maybe some door and window sensors and also the camera sensor, right? There's such kind of anomaly. We need to push that to the customer. And also there's some special events for some customer, they want to detect the package delivery. So we think that as a special event, we have to detect it. So yeah, so there's still computer vision based techniques like activity recognition.
Great, thank you, Hongcheng. Nice job, very nice job.